We live inside a narrow band of sensation. Warmth and cold feel simple to us because our bodies keep a private balance, and the world around us usually stays close enough to it to make sense. But beyond that familiar range, temperature stops being a feeling and becomes a quieter, stranger question. One that depends on motion we cannot see, on particles that may be absent, on light that may never arrive. Space looks like an empty stage, yet emptiness has its own rules. It can cradle heat for a long time or erase it quickly. It can appear colder than anything we can build on Earth, while still carrying a faint, persistent glow that no darkness fully escapes. Even the stars, those steady furnaces, are surrounded by regions where the idea of cold becomes hard to define at all. Tonight, we will follow temperature outward from the human scale into the cosmic one, until cold is no longer a number we recognize, but a boundary that shapes how the universe behaves. And by the end, the question will feel less like a curiosity and more like a map of what reality allows. It begins with what we mean when we say something has a temperature. Temperature is one of those words that seems to belong to the skin. It feels like a truth you can confirm with a palm against a window, a cheek near a cup, a breath in winter air. But the moment you try to carry that feeling into space, the word begins to lose its old shape. Out there may be nothing to touch you back, no surface to borrow warmth from, no air to carry it away. And yet the universe still speaks in temperatures, as if cold and heat are written into reality, even when no one is there to feel them. To understand that language, you have to let temperature become impersonal. Not comfort, not suffering, not the simple idea of hotter or colder. Temperature is a way of describing motion that is too small to see. In the crowded world near Earth, every substance is a busy crowd of particles, atoms and molecules in constant movement, colliding, trading speed, sharing energy. When a material is warmer, its particles are, on average, moving more quickly. When it is colder, they move more slowly. The difference is not a color or a mood, it is a statistical pattern. Heat, then, is not temperature itself. Heat is what moves between places when that pattern is uneven. If two objects touch, their particles collide across the boundary and exchange energy. The faster ones tend to slow down. The slower ones tend to speed up. Given time, the two patterns blend into one, and the temperatures meet somewhere in between. This is why a metal railing can feel painfully cold at the same air temperature as a wooden door. The metal is not necessarily colder, it is simply better at pulling energy out of your skin, carrying it away through its own internal crowd of particles. Your nerves report the speed of that loss, not the number on a thermometer. A thermometer itself is a quiet negotiation. It does not sense temperature as a separate substance. It reaches a balance. In a glass tube, a liquid expands or contracts as its internal motion changes. In a digital probe, electrons respond to the agitation of atoms in a metal. Every measurement is really an agreement. The thermometer and the thing it touches come to a shared condition, and the device displays what that shared state implies. But space does not offer contact easily. Remove the air from around an object, and conduction almost disappears. There are fewer particles to collide with, fewer messengers to carry energy into or out of a surface. Take the vacuum deep enough, and touch becomes a rare event. The old, familiar pathway of cooling, warmth leaking into surrounding air, stops being the main story. In that silence, temperature becomes harder to picture because it is no longer tied to the speed of exchange. In a near vacuum, a warm object can keep its heat for a long time if it is insulated from contact. It can also lose heat steadily if it can radiate it away. Radiation is different. It does not require a medium. It is energy leaving as light, sometimes visible, often infrared, sometimes at wavelengths your eyes were never built to notice. Every object above absolute zero emits some amount of electromagnetic radiation. The warmer it is, the more it emits, and the spectrum shifts. This is not a metaphor. It is a physical pathway by which energy can leave without a single collision. Now the idea of space temperature begins to split into several meanings. The temperature of a solid object, like a spacecraft panel, depends on how much radiation it absorbs and how much it emits, as well as whether it has internal heat sources and how it shares energy through its structure. Meanwhile, the temperature of a gas, if gas exists at all in that region, describes the average kinetic energy of its particles. And the temperature of the radiation field itself describes the distribution of photon energies passing through, even if those photons rarely meet anything. These are not interchangeable. You can place an object in a region where the gas temperature is extremely high and still have the object remain relatively cool if the gas is so sparse that collisions are rare. A thin plasma can contain particles moving at extraordinary speeds, yet carry almost no total heat content simply because there are so few of them. In everyday life, high temperature and high heat content often travel together because our world is dense. In space, density can be so low that temperature becomes a kind of ghost statistic. A description of motion that does not necessarily translate into the power to warm anything. This is where intuition often fails. It expects temperature to behave like a single dominating condition. But in the cosmic environment, temperature is local and selective. It depends on what you are asking about. A molecule, a dust grain, a beam of radiation, a surface in shadow. Each can occupy the same region of space and yet live in a different thermal story. To say space is cold is usually to speak about what happens when something tries to shed its energy into the environment. In darkness, far from strong sources of light, an object radiates away heat and receives little in return. Over time, it cools toward a balance set by whatever background radiation remains. But if you describe that same darkness by the temperature of its gas, you might find a different answer. Because the gas could be heated by cosmic rays, by distant starlight, by shock waves, by magnetic processes. Even a few energetic particles can keep the average speed of a sparse gas high while leaving an object nearly untouched. The idea of cold becomes even stranger when you remember what absolute zero really is. It is not a special kind of darkness. It is a limit defined by motion. At absolute zero, particles would have their minimum possible energy. Classical intuition imagines complete stillness. Reality is subtler. The quantum world does not allow perfect rest in the way our minds prefer to picture it. Even in the lowest energy state, there can be residual motion, an unavoidable jitter written into the rules. So when we speak of approaching absolute zero, we are approaching a boundary defined not by emptiness, but by the structure of physics itself. And yet, even with that boundary in mind, the practical meaning of cold in space is often determined by radiation, not by a fantasy of perfect stillness. Light fills the universe. Some of it is obvious, the glare of stars, the wash of galaxies. Some of it is faint and ancient, spread thin across all directions. Even where matter is almost absent, photons continue to pass through, carrying energy. A region may look black to human eyes, but blackness is not the same as zero. There can be a dim bath of long wavelength radiation, a quiet presence that sets a floor under how far cooling can go for objects that absorb and emit. So the question, how cold can space become, is not only a question about distance from stars, it is also a question about definitions. Cold for what? Gas? Dust? Radiation? A human-made instrument? Cold over what timescale? Minutes? Centuries? The life of a molecule drifting between clouds? And cold under what conditions? Exposed to the sky? Hidden in shadow? Surrounded by particles that almost never meet? On Earth, temperature is a shared reality. The air, the ground, the ocean, the living body, they are constantly colliding, constantly averaging each other out. In space, temperature can fragment. Energy can remain trapped in one form while absent in another. A single region can hold fast particles and cold surfaces, hot ions and frigid dust, all coexisting because the pathways that would normally bring them into agreement are too slow or too rare. What begins to emerge is a quieter definition of emptiness itself. The coldest places are not simply those farthest away. They are the places where energy has the fewest ways to arrive and the most time to leave. They are the places where contact is scarce, and radiation is the only steady conversation. Out there, when contact becomes rare, even the simplest act of cooling starts to depend on geometry. An object does not cool because space is cold. It cools because it can see a sky that offers little incoming radiation, and because it has a way to shed its own energy into that view. If it faces a star, it warms. If it turns away, it cools. If it is shaded by a planet, a hull, a rock, it cools further still. Temperature becomes something like a quiet relationship between surfaces and what they are exposed to, rather than a single environmental condition. This is why a spacecraft can carry two very different climates at once. A sunlit panel can become hot simply by absorbing light, while a nearby shaded component radiates its heat away and falls toward a far lower equilibrium. Between them, the metal frame conducts some energy, but conduction is now an internal conversation, not one held with a surrounding void. The environment is not an ocean of air pressing against every surface. It is mostly a view, an exposure to radiation. And yet, even the darkest view is not empty. Space contains a persistent background of photons. They are not concentrated like starlight. They arrive from every direction, evenly enough that the effect can feel like a faint thermal presence. If a perfect absorber sat alone and waited long enough, it would come into balance with that photon bath, neither gaining nor losing net energy to it. The temperature that corresponds to this background is low, but not zero, and it does not depend on where you are within the universe. It is part of space itself, a remnant of an earlier, denser epoch when light and matter were more tightly coupled. This changes the nature of the question. The coldest possible space is not simply the deepest shadow behind an object or the farthest intergalactic void. For most ordinary matter, the floor is set by what remains unavoidable, the faint radiation that permeates the cosmos, plus any other rare inputs, passing starlight, energetic particles, the occasional collision with a stray atom. The coldest reachable state is a balance between almost nothing arriving and something always leaving. But the universe complicates even that, because nothing arriving is not uniformly true. Space is threaded by fields and by particles that do not behave like air. Cosmic rays, for instance, are fast particles, often protons or atomic nuclei, moving through the galaxy with enormous energies. They are sparse, but when they collide, they can be transformative. A single hit can deposit a burst of energy into a grain of dust, heating it briefly, and then the grain cools again by radiating. The average temperature of a dust population can be low, while individual grains experience sudden momentary spikes. In the human world, such fluctuations are smoothed out by dense surroundings. In the cosmic world, the punctuated nature of energy exchange can remain visible. Meanwhile, gas, thin, tenuous, barely a presence, can carry a temperature that sounds contradictory when translated into everyday language. In a region where there are only a few particles per cubic centimeter, those particles can still be moving rapidly. Temperature, after all, is an average kinetic energy. A sparse plasma can be hot because its few particles have been accelerated by magnetic turbulence or shocks, even though it contains so little total energy that it cannot easily warm a solid object. To a spacecraft passing through, the sensation would not be that of a hot bath. Collisions would be too infrequent. Heat transfer would be minimal. The gas's temperature would be real and measurable, yet it would not behave like heat does in air. This is the first quiet lesson of cosmic cold. Temperature is not the same as warmth. Warmth is what a system can give you through interaction. Temperature is a description of internal motion that may remain mostly locked within itself. If you want to know how cold space can become, you have to decide which kind of temperature you mean. The temperature of the radiation field is one kind, setting a baseline glow. The temperature of gas is another, sometimes high even where matter is scarce. The temperature of solids and dust is yet another, shaped by how they absorb and emit, and how often they are disturbed. And because we cannot travel to most of these regions, because we cannot place thermometers there and wait for them to settle, we infer temperature in the way astronomy infers nearly everything, by reading light. A gas reveals itself through spectral lines, specific frequencies that correspond to transitions in atoms and molecules. Those lines can broaden if particles move faster, and the distribution of populations among energy states depends on how often collisions occur and what radiation is present. From these details, scientists can estimate kinetic temperatures, excitation temperatures, and other thermal descriptors that become necessary precisely because space refuses to provide a single, shared equilibrium. The same cloud can host molecules that behave as if they are cold in one sense, while electrons in the same region act far hotter. Measurement becomes a careful act of interpretation, not a single number, but a portrait of how energy is partitioned. Dust, too, speaks through radiation. Tiny grains absorb starlight and re-emit it at longer wavelengths. The peak of that emission shifts with temperature, and the intensity reveals how much energy the dust is processing. In the darkest molecular clouds, far from bright stars, dust can cool to remarkably low temperatures, limited by the faint background and by occasional heating events. These environments are among the coldest places where matter collects, because they are both shielded and dense enough to block external radiation, yet still cold enough that chemistry slows and motion becomes quiet. But even there, cold is not absolute. A dense cloud is not a perfect refrigerator. It can hide from starlight, but it cannot hide from the background glow of the universe, and it cannot fully insulate itself from particles that penetrate. It can become a pocket where radiation is filtered down to long wavelengths, where dust and gas drift toward a low equilibrium, and where the pace of thermal exchange becomes almost geologic. On the opposite extreme, the emptiest regions between galaxies, the vast, thin voids, seem at first like candidates for the coldest places. If there is almost no matter and few nearby stars, what could keep anything warm? But emptiness comes with its own twist. In a void, there may be little to absorb radiation, but also little to emit it. If there is nothing to cool, the void cannot be colder in the sense we intuitively mean. Temperature requires a system. The coldest place is not a coordinate in space. It is the coldest state a piece of matter can achieve under the ambient conditions there. In these intergalactic regions, the dominant temperature one can meaningfully assign might be the temperature of the radiation field itself, because that is what is uniformly present. Meanwhile, the few particles that do exist may be influenced by large-scale structures, shocks from the growth of cosmic webs, the faint ultraviolet background from distant galaxies, the slow heating from energetic events. The result can be counterintuitive. Matter can be warmer in the emptiest spaces than in a shaded, dense cloud, simply because a cloud can shield itself and radiate efficiently, while diffuse gas can be kept energized by processes that do not require density. Cold, in the cosmos, is often made not by emptiness alone, but by isolation plus the ability to radiate, by being able to lose energy while blocking what would replace it. This is why shadows matter. Not metaphorical shadows, but literal ones, cast by bodies and structures. Near a planet, a spacecraft in eclipse can cool rapidly because the planet blocks sunlight, and the craft now radiates into a sky that offers little return. Yet the planet itself is not a source of cold. It is a source of infrared warmth. An object near Earth is warmed by Earth's emitted radiation, even on the night side. The same is true near other worlds. A dark planet is not dark in thermal terms. It is constantly shedding the heat it has stored and the energy it receives. In close proximity, that infrared glow can set a higher floor than the cosmic background ever could. So the coldest environments are not necessarily found near planets, or even near stars, because nearby objects tend to fill the sky with thermal radiation. To find deeper cold for matter, you often need distance and shielding. Distance from strong radiators and shielding from starlight. The most effective cold is made in regions where the sky, from the perspective of a particle or a grain, is mostly a cold sky. And yet, there remains an even deeper tension in the idea of coldest possible. Even if you could remove every star from view, even if you could place an object in perfect shade and wait, it would still exist in a universe that contains that faint background glow. It would drift toward equilibrium with it, settling into a temperature that reflects the energy of those omnipresent photons. That background is not merely a detail, it is a kind of cosmic memory. It means the universe carries a residual warmth not because it is actively heated everywhere, but because it began in a state where energy was dense and shared. As the universe expanded, that radiation stretched and cooled. The coldness of space, in this sense, is not a static property. It is a slow consequence of cosmic history, a temperature that has been dropping for billions of years as the fabric of space has grown larger and the same light has been diluted and redshifted into longer wavelengths. If you keep following that thought, the coldest possible space becomes tied to time as much as to place. As the universe continues to expand, the background radiation will continue to cool. The baseline temperature of space, defined by that pervasive photon field, will slide lower and lower. But it will do so slowly, in a way that cannot be rushed by shielding or insulation. It is not an engineering problem, it is a cosmological trajectory. Even that trajectory does not guarantee an approach to perfect zero. Quantum principles put constraints on how still matter can become, and the universe is not a sealed laboratory. There are always processes that inject energy: decays, collisions, stray radiation, the slow stir of gravitational interactions. Absolute zero remains less like a destination and more like a mathematical horizon, something that defines direction without offering arrival. This is why the question in the title carries a quiet depth. How cold can space become is not only asking for a number. It is asking what it means to be cold in a universe where energy can hide in different forms, where motion can persist without touch, and where emptiness is never fully empty. It asks where the universe allows stillness, and where it insists on movement, even in its most remote corners. By the time the word temperature has been stripped of its human skin and returned to its physical roots, cold is no longer simply the opposite of heat. It is a boundary condition for matter, chemistry, and the long future of cosmic structures. It is a measure of how the universe shares energy, and how it refuses, in certain places, to share at all. And in that reframing, the most familiar sensation, cold air on the face, has quietly expanded into something vast, a way of reading the universe's limits, written not in drama, but in the gentle mathematics of motion, radiation, and time. The mind is built for weather, not for vacuum. It is tuned to a world where warmth moves through air, where cold arrives as a wind, where the difference between shade and sun is immediate and bodily. We carry an internal scale calibrated by skin and breath, by metal that bites the hand in winter, by stone that holds the day's heat into evening. When we try to apply that scale to space, we tend to imagine a single universal cold, an endless freezer surrounding the stars. It is a natural picture, and it is almost always wrong. Our most persistent mistake is to treat temperature as a property of place, like altitude or distance. On Earth, this works well enough. A valley is warmer than a mountaintop. The air is cooler at night than at noon. The atmosphere mixes, surfaces exchange heat with it, and the whole system stays knitted together by constant contact. Space does not offer that knitting. Without a medium to distribute energy, conditions can diverge sharply within arm's length, and ambient temperature becomes a slippery phrase. In the mind's theater, cold means rapid loss. You step outside and your body begins to drain its heat into the air. But that draining is not simply because the air is cold. It is because the air is dense enough to carry energy away by endless collisions. In near vacuum, the opposite can happen. A warm object can stay warm longer than intuition expects, not because the environment is warm, but because the main pathway you associate with cooling is missing. The mind confuses a lack of warmth with an active force of cold, as if cold were something that reaches in and grabs heat. In reality, cooling is usually an escape route, not an attack. Another cognitive habit follows us into the dark. We imagine emptiness as perfect stillness. We picture a region with no matter as a region with no energy, and we quietly equate that with absolute zero. But no matter does not mean no influence. Light crosses space even where atoms are scarce. Fields extend without needing particles as carriers. A place can be almost empty and still be threaded by photons, by magnetic structures, by passing particles moving too fast to be counted as a background. Emptiness is not an end state. It is a different kind of environment, one that breaks the shortcuts our brains prefer. Part of the confusion comes from the way the word temperature is used in ordinary life. We use it as if it were the same thing as warmth, or the same thing as heat content, or the same thing as how dangerous a place might feel. In a dense room, these meanings overlap. In space, they separate. The temperature of a gas can be high because a few particles are moving quickly, but if there are too few collisions, that gas can hardly warm anything. It can be hot in the statistical sense and still be incapable of cooking, melting, or even noticeably warming a nearby surface. The mind wants one number to rule the scene. The cosmos does not oblige. So we need a mental framework that does not lean on touch. The first step is to accept that, in space, the dominant thermal relationship is often between an object and the radiation it sees. Surfaces gain energy by absorbing light and lose energy by emitting it. Shade and sunlight become more important than air temperature because there may be no air. The body understands shade as a relief. In space, shade can be a deep cooling mechanism, while sunlight can turn a surface into an oven. The same object can have a blistering side and a frigid side, not because space is inconsistent, but because the object's view of the universe is different in different directions. The second step is to accept that cold is not always experienced as cold. The idea sounds simple, but it is the hinge on which much misunderstanding turns. If you were somehow placed in a vacuum, you would not feel cold in the way you feel it on Earth. Without air, there is no convective wind pulling heat from your skin. Your body would still lose heat, but mostly by radiation, and radiation is slower than the draining you associate with a winter night. The true danger would not arrive as a clear sensation. It would arrive as a mismatch between what the body expects and what physics allows. The mind wants a feeling to warn it. Space offers processes instead. A third step is to abandon the notion that space has a single background state. Even within the same region, there can be multiple temperatures describing different aspects of the environment. The radiation field can be characterized by a temperature that reflects the distribution of photon energies. The gas can have a kinetic temperature based on particle motions. Dust grains can have their own equilibrium temperatures based on what they absorb and emit. These temperatures can disagree, and the disagreement is not an error. It is a signature of weak coupling, a sign that the pathways that would normally force them to converge are too slow. This is where human perception reaches for its most familiar crutch, the idea of balance. On Earth, balance is everywhere. A cup of coffee cools until it matches the room. A stone warms until it matches the sunlit air. When systems interact frequently, equilibrium becomes the default. In space, equilibrium can be rare and local. A molecule might spend years without colliding with another molecule. A dust grain might drift through a dim region, cooled almost entirely by its own radiation, disturbed only occasionally by a passing energetic particle. If you asked for the temperature of that environment, you would have to specify what you mean by thermal balance, because the usual assumptions no longer hold. The mind also struggles with scale, not just in distance, but in time. On Earth, thermal changes are usually quick enough to register. Put your hand near a flame and you feel it immediately. Step into shade and you cool within moments. But in space, cooling can be slow, simply because radiation is a gentle method of exchange and because many objects are well insulated by vacuum itself. A warm object can take a long time to lose its stored heat if it cannot conduct it away. Meanwhile, a sparse gas can take a long time to share energy among its particles if collisions are rare. The pace of thermal life can stretch out until cause and effect drift apart and the mind loses its grip. Even our language conspires against us. We say, space is cold, as if cold were a substance that fills it. We speak of the temperature of space, as if space were a room with a thermostat. These phrases are useful shorthand, but they hide the more accurate picture. Space is a place where the usual carriers of heat are missing, where radiation becomes the main exchange, and where temperatures depend on what you are measuring and how strongly it is connected to everything else. If you want to sense the scale of the problem, consider how easily the mind confuses brightness with heat. A bright star looks like warmth. A dark void looks like cold. But brightness depends on the sensitivity of your eyes and the wavelengths they can see. The universe can be visually dark while still filled with infrared radiation, microwave photons, and other forms of light that carry energy. A region that looks empty can still be bathing an object in a faint glow that matters over long timescales. Our perception is selective. The cosmos is not. There is also a subtler limitation, one rooted in how we imagine extreme. When we hear that something is incredibly cold, we instinctively picture an intensification of familiar cold, a deeper winter, a sharper wind. But cosmic cold is not simply colder air. It is a different regime of physics, where the lack of collisions changes everything from chemistry to the way energy flows. At low temperatures, molecules settle into their lowest rotational and vibrational states. Reactions slow or stop. Materials behave differently. And in very sparse environments, those low-energy states can persist for long periods because there are so few opportunities for disturbance. Extreme cold is not just an intensity, it is a change in how systems behave. To keep our footing, we need a calmer way of thinking. Not a single thermometer reading, but a set of relationships. How often do particles meet? How much radiation arrives? What wavelengths dominate? How well an object absorbs and emits? How much time it has to drift toward equilibrium? These are quiet questions, and they fit the universe better than our instinctive search for a single headline number. When you adopt that framework, cold space begins to look less like a uniform abyss and more like a patchwork of thermal stories. Near a star, radiation can dominate. In the shadow of a dense cloud, cold can deepen. In a thin plasma, kinetic temperatures can soar without bringing warmth. In the deep background, a faint universal glow sets a floor that is present everywhere, even where darkness seems complete. The mind wants simplicity. The cosmos offers context. And perhaps the most humbling limit is this: we cannot directly experience most of these conditions. We cannot step into a molecular cloud or drift in the void between galaxies and feel what it is like. We rely on inference, on instruments that translate invisible motions into numbers, on models that tell us how energy should be distributed when contact is scarce. Our understanding of cosmic cold is therefore always mediated. It is a form of knowledge that lives in translation, and the act of translation is itself part of the story. Because once the mind accepts its own limits, it becomes capable of a more precise kind of wonder, one that does not demand that space behave like Earth, and does not insist that cold feel like cold. It allows the universe to be stranger in a quieter way, and it prepares us to follow the measurements that make that strangeness legible. There is a particular kind of discomfort that arrives when intuition is removed. Not fear, not excitement, but a soft disorientation, like walking into a dark room you know well and finding the furniture moved. In space, temperature does this to the mind. It rearranges the familiar. It takes a word that usually belongs to the body and asks us to hold it as an abstract property of motion, radiation, and probability. The discomfort is not a flaw in understanding. It is the moment the mind realizes the universe is not scaled to human senses. One of the most revealing places to feel that shift is in the idea of the coldest. The mind expects a single location, a single answer, a deepest point you could reach if you traveled far enough away. But in the physics of space, cold is often less about where you are and more about what is happening to a system. It is a state you approach under certain conditions. If those conditions change, if a faint light source rises, if a particle strikes, if a surface rotates into sunlight, the state changes. Cold is not a final destination. It is a balance that must be continuously maintained. This forces a more careful question. What does it mean for something in space to have a temperature at all? In a dense environment, temperature is meaningful because countless collisions rapidly distribute energy. A thermometer placed there settles because the system itself is already well mixed. But when collisions are rare, temperature can become a thin description, useful but incomplete. A single particle might carry a great deal of energy, while its neighbor carries very little, and nothing forces the two to share. If you tried to define an average, you might get a number, but the number would hide the fact that the system is not truly thermalized. In that setting, temperature becomes less like a property and more like a shorthand for a distribution that may not be stable. The mind wants equilibrium because equilibrium is predictable. It is the state where the world stops changing quickly, where you can say, "This is the temperature," and trust it. Space teaches a slower lesson. Many cosmic environments live in partial equilibrium, or in layered equilibria that depend on what you measure. A dust grain can settle into a stable temperature based on radiation, while the gas around it remains out of equilibrium because collisions are too infrequent to distribute energy. A molecule might have a rotational state population that implies one temperature, while its translational motions imply another. None of this is error. It is the imprint of thinness, of a universe that often does not have enough contact to become simple. Once you accept that, you can see how the mind's everyday metaphors quietly mislead. We imagine heat as a fluid, cold as a vacuum that pulls it in. We imagine temperature as a level that rises and falls. These images are not entirely wrong, but they are too smooth. In space, thermal life is granular. Energy arrives in packets, photons, collisions, sporadic impacts. It leaves as radiation, sometimes continuously, sometimes in bursts. The environment is not a bath, it is a sky. Even the concept of insulation shifts meaning. On Earth, insulation works by trapping air and slowing convection. In space, there is no air to trap. Insulation becomes a matter of controlling radiation and internal conduction. Reflective surfaces, multi-layer blankets, careful geometry. What matters is not how thick something is, but what it sees and what it emits. A surface that looks out into open space can cool, while a surface facing a warm object, even a distant one, can be gently heated by its infrared glow. The mind is tempted to think of space as universally cold and therefore a perfect coolant. In practice, cooling in space is an art because the universe is not uniformly cold in radiative terms. Sunlight, reflected light, planetary warmth, and internal heat sources can all compete. This leads to a more delicate appreciation of shadow. On Earth, shadow is mostly a visual concept, a soft dimming. In space, shadow can be thermal architecture. It can create pockets where radiation is blocked, and objects radiate away their heat into a darker sky. But even there, shadow is not absolute. Light diffracts. Radiation arrives from multiple directions. A warm body nearby fills part of the sky with infrared emission. The coldest possible view is not simply no direct sunlight. It is a view dominated by the faintest backgrounds, a direction that offers as little incoming energy as the universe allows. And that brings the mind to another limit, the selective nature of perception. We see a narrow slice of the electromagnetic spectrum. We associate darkness with the absence of energy because our eyes report nothing there. Yet space is rarely silent in every wavelength. A region can be visually empty while still carrying long wavelength radiation that contributes to thermal balance over long times. If you were to stand, imagining, not physically, inside such a region, your eyes might tell you it is perfectly black. But a sensitive detector might see a wash of microwaves, a faint infrared haze, a spectrum that never fully vanishes. The mind has to learn that dark is not a synonym for cold, and cold is not a synonym for nothing. When the language of temperature becomes abstract, it also becomes connected to time in a way we seldom notice on Earth. Cooling by radiation is relentless but gentle. The rate depends on temperature itself. Warmer objects radiate more powerfully, cooler ones more weakly. As something cools, it cools more slowly. Approaching extreme cold is not a straight descent. It is an ever-lengthening process, like walking into a fog that thickens as you move. The mind expects a finish line. Physics offers an asymptote. In the cosmic setting, this slow approach can become a defining feature. A dust grain drifting in a sheltered region can take a long time to settle into its equilibrium temperature, and even longer to respond to small changes in its radiative environment. A cloud can remain cold for extended periods because the pathways for heating are weak and intermittent. Temperature becomes a kind of long memory, especially for systems that are isolated. This is another point where intuition stumbles. We often imagine that if a place is cold, it must be actively making things cold. But cosmic cold is frequently passive. It is the absence of heating more than the presence of cooling. The universe does not manufacture cold the way it manufactures light. It allows energy to leak away when nothing replaces it. That is why coldest is so often tied to shielding, not to emptiness alone. A region can be dense enough to protect itself from starlight, yet still thin enough that collisions are rare and energy exchange is limited. In that combination, shielding plus isolation, cold can deepen. The mind also tends to treat extremes as rare, as exceptions. Yet, in the universe, extremes are often the norm. Most of space is not like the surface of a planet. Most matter is not organized into thick atmospheres and oceans. The conditions we evolved in are a specialized corner of cosmic possibility. Recognizing this is not meant to shrink the human scale, but to place it accurately. It clarifies why our instincts mislead. They were never meant to navigate a reality where heat moves primarily through radiation and where equilibrium is optional. And still, despite these limits, the mind can adapt. It can trade sensation for structure. It can learn to ask better questions. Instead of, "How cold is space?" it can ask, "What is exchanging energy here, and how?" Instead of picturing a universal freezer, it can picture lines of sight and spectra, collisions and their absence, the slow interplay between emission and absorption. This is not a colder way of thinking, it is a more spacious one. In that spaciousness, an unfamiliar clarity appears. The universe is not indifferent to temperature. Temperature shapes what can form, what can persist, what can change. It governs the quiet chemistry of clouds, the stability of dust, the behavior of plasmas, the ability of matter to gather and cool and condense. Even the emptiest places carry a baseline glow, and even the densest dark clouds are shaped by what radiation can penetrate them. Cold is not merely a curiosity, it is a condition that organizes the cosmos at every scale. But to follow that condition faithfully, we must keep remembering the mind's limits. We must resist the urge to compress everything into a single number, to treat temperature as a uniform atmosphere, to imagine that darkness is emptiness, and emptiness is absolute zero. The universe does not meet us on those terms. It offers instead a quiet complexity, different carriers of energy, different time scales of exchange, different definitions that remain valid side by side. And perhaps the most calming part of that complexity is that it removes the need for dramatic imagery. Space does not have to be a freezing monster or a burning void. It can simply be what it is, a realm where energy travels differently, where temperature becomes a layered concept, and where our instincts, so useful on Earth, must be gently set aside. In that setting, understanding does not arrive as a sudden insight. It arrives as a steadier shift in posture, the mind learning how to stand in a universe that does not touch back. And once it finds that stance, the question of cold becomes clearer. Not because it becomes simpler, but because we stop asking it in human terms and start asking it in cosmic ones. A star does not simply shine. It negotiates with everything around it. It sends energy outward in waves of light, in streams of charged particles, in subtle changes to the surrounding fields. And the space that holds that energy is not an empty container. It responds, reshapes, and redistributes what it receives. If the universe has any quiet paradox, it is this. The same star that makes warmth possible can also help carve out regions where cold becomes profound. Near a star, heat begins as a private violence deep inside matter, hidden beneath layers that keep fusion out of sight. Yet what reaches space is not violence, it is radiation, patient and constant, traveling outward at a speed that does not slow for emptiness. The star's light is not merely illumination, it is energy in transit, and wherever it lands, it changes the thermal story of whatever receives it. A grain of dust drifting in the outer reaches of a stellar system is small enough to cool quickly, yet large enough to be affected by a single photon's arrival. When starlight strikes, the grain absorbs energy and its internal motion increases. Then, almost immediately, it tries to give that energy back, radiating it away at longer wavelengths, often infrared, invisible but real. Its temperature becomes a balance between incoming light and outgoing emission. It does not care how cold the surrounding vacuum might be in a conversational sense. It cares what it sees and what it can shed. This is one of the first ways stars create heat around them without heating the space itself. The vacuum does not warm like air. Space does not store warmth in the same way. What changes is the temperature of matter within that space, depending on exposure. A dust grain in direct starlight can be relatively warm. Another grain, only a short distance away but sheltered behind a dense clump of gas, can cool to far lower temperatures, even though both occupy the same region. The star sets the rules, but geometry decides the outcome. The star also heats space in a second, less intuitive way, by changing the state of gas. When high-energy ultraviolet light strikes an atom, it can tear electrons away, creating ionized regions where particles are charged and responsive to magnetic fields. These ionized zones can be extremely hot in terms of particle motion. Yet again, the word hot can be misleading. The gas may be so thin that, despite its high temperature, it cannot easily transfer heat to a solid object. Its particles move quickly, but the gaps between collisions are vast. Temperature describes motion, but motion without contact is not the same as warmth. Still, that motion matters. It changes pressure, and pressure shapes structure. Ionized gas expands. It pushes against surrounding material, carving cavities and fronts, regions where the star's influence is not simply radiative, but architectural. The heat around a star, then, is not only a matter of numbers on a scale, it is a mechanism that sculpts the environment, thinning some regions, compressing others, and creating the varied landscapes in which cold can later form. If light is one channel of stellar influence, wind is another. Stars release streams of particles, stellar winds, that carry momentum outward. In some stars, this wind is gentle, in others, fierce. But in all cases, it is a transfer of energy that does not require the presence of air. These particles collide with interstellar gas, stir magnetic fields, and create shock boundaries where motion is abruptly reorganized. A shock can raise the temperature of gas dramatically by converting bulk movement into random motion. Again, the environment can become hot in the kinetic sense, while remaining incapable of warming objects in the way a hot atmosphere would. But the shock still changes chemistry, still changes radiation emission, still writes patterns into the surrounding medium. In the regions where winds and radiation dominate, the idea of space temperature becomes a tapestry. There are layers. The star's photosphere radiating outward, the corona, astonishingly hot in terms of particle energies, the outward wind expanding and cooling as it travels, the interplanetary or interstellar medium interacting at boundaries, and beyond that, the larger background the star exists within. At each layer, different processes set the terms of thermal balance. There is no single gradient from hot to cold. There are competing mechanisms, overlapping domains, and places where one dominates because the others fade. One of the most important quiet processes here is expansion cooling. When gas expands into a lower pressure region, it can cool even without losing energy to the outside. Its internal energy spreads out as it does work in expansion. This is not a dramatic event. It is the natural behavior of gas allowed to thin. Around stars, outflows expand, winds expand. Heated regions expand into surrounding space. In doing so, they can cool, sometimes quickly, creating pockets where temperature drops even as the star continues to shine nearby. The star supplies energy, but the environment has ways of diluting it. Dust, too, participates in a slow cooling story. While gas can carry heat in its particle motions, dust often becomes the primary radiator in cold regions. Dust grains absorb starlight and re-emit in the infrared, effectively converting higher energy photons into a gentler, longer wavelength glow. In dense environments, where gas and dust collide more often, they can share energy and approach a more unified temperature. In thinner environments, dust and gas can diverge. Dust might cool efficiently by radiation, while gas remains warmer due to other heating mechanisms. The result is a separation of thermal realities that feels alien only because Earth rarely allows such separation to persist. What makes the heat around stars secret is that it is often indirect. We imagine a star warming everything nearby as if it were a campfire. But most of the region around a star is not warmed by touch. It is warmed by the absorption of radiation, by the excitation of atoms, by the rearrangement of particles. Even within a planetary system, objects do not share temperature simply because they share space. They share temperature only through exchange, and exchange depends on distance, reflection, rotation, shadow, and material properties. Consider a small body, an asteroid, spinning slowly in deep space. One face turns toward the star and absorbs light, warming. The other face turns away and radiates its heat, cooling. If the rotation is slow, the contrast can be extreme. A hot day side, a cold night side, each existing in equilibrium with what that side can see. The asteroid is not immersed in a consistent ambient condition. Its surface temperature is literally drawn by angles. Even the space between bodies has its own complexity. Near a star, the gas can be heated by photoionization and by interactions with winds. But as you move outward, the density drops, collisions become rarer, and the gas can decouple from the radiation field in certain ways. It can remain energized by sporadic processes, cosmic rays, magnetic turbulence, shocks, while still being too thin to share that energy efficiently. In this regime, the mind's simple expectation that distance from the star equals colder conditions fails gently but decisively. Yet, despite this complexity, the star still provides the central axis of the thermal story. It is the dominant energy source, and its spectrum matters. A star emitting more of its energy in higher frequencies interacts differently with surrounding gas and dust than a cooler star with a different spectrum. Ultraviolet-rich light can ionize and heat gas more effectively. Softer light may heat dust more gently. The character of heat around a star is written not only in luminosity, but in the distribution of that luminosity across wavelengths, and therefore in what kinds of matter can absorb it. This is why the coldest places in a stellar neighborhood are often not simply far away, but hidden. They are inside dense clouds, where starlight is filtered and scattered until only long wavelengths remain. They are in the deep shadows cast by thick regions of dust and gas, where the sky becomes thermally dim. They are in pockets where radiation is blocked, where expansion has thinned and cooled gas, where dust radiates away energy into a view that offers little return. The star is still present, still shaping the environment, but its energy is prevented from arriving in the forms that would keep those pockets warm. If you follow that thought, you begin to see the star not as a simple heater, but as a creator of contrasts. Its light raises temperatures where it lands, but by doing so, it also drives motions that clear space, compress clouds, and build structures that cast longer shadows. It stirs the medium into cavities and shells, and in the sheltered parts of those structures, cold can take hold. The star's power is not only in heating, it is in the rearrangement that makes heat uneven. This unevenness is not a flaw, it is the engine of much of cosmic evolution. Where temperatures differ, pressures differ. Where pressures differ, gas moves. Where gas moves, it can condense, fragment, and change. Around stars, the thermal landscape becomes one of gradients and boundaries, and within those boundaries lie the conditions for both warmth and deep cold. In the calm distances beyond a star's immediate glare, the most revealing thing is not the warmth that remains, but the way warmth becomes selective. The universe does not spread heat evenly, It sends energy along paths, and those paths depend on what can absorb, what can reflect, and what can hide. Around a star, this creates a kind of thermal geography: bright slopes and dark valleys, exposed ridgelines and sheltered basins, drawn not by terrain, but by radiation. One of the quietest shapers of that geography is opacity, the simple question of what light can pass through. A thin veil of gas may be nearly transparent to visible light, yet absorb strongly in ultraviolet. A denser curtain of dust may block starlight across many wavelengths, while allowing longer infrared radiation to seep through. In the regions where stars are born, opacity becomes an architect. It determines which parts of a cloud are heated, which remain cool, and how sharply those zones are divided. The star's energy is constant, but the medium does not accept it uniformly. As starlight enters a dusty region, it does not merely fade, it changes character. Shorter wavelengths are absorbed and re-emitted as longer ones. The energy is not destroyed, but it is redistributed into a spectrum that matters differently to matter. Ultraviolet photons that might ionize gas are converted into infrared photons that mostly warm dust. The cloud becomes a filter, turning the star's sharp light into a softer thermal glow. Deeper inside, even that glow weakens. The sky, from within the cloud, grows dim in a radiative sense. It is there, shielded, muffled, insulated by its own density, that cold can become stable enough to shape chemistry and structure. In these hidden interiors, the idea of heat around stars becomes almost inverted. The presence of a star nearby does not guarantee warmth. If the star's light cannot penetrate, the cloud can cool toward a low equilibrium set by whatever radiation does reach it and by what the cloud itself emits. Dust becomes both absorber and radiator, quietly bleeding energy away. Gas can cool by emitting in specific molecular lines, radiating energy in narrow frequencies that escape into space. Cooling here is not an act of contact, but an act of emission. Matter losing energy by letting light carry it away. Yet even this cooling is not absolute. A cloud can hide from starlight, but it cannot hide from every influence. Energetic particles can pass through more easily than photons. Rare interactions can deposit energy deep inside, keeping some fraction of the gas from settling into perfect stillness. Turbulence can stir material, converting organized motion into random motion. Gravity itself can become a heating process. As matter slowly collapses, potential energy transforms into kinetic energy, and kinetic energy can become heat. Around stars, cold and heat are not separated by distance alone. They are interwoven by the competing processes that govern the life of gas and dust. Even in the more open regions of a star's domain, the thermal story is never smooth. Consider the boundary where a stellar wind meets the surrounding interstellar medium. There, moving particles pile up and a shock can form. A surface without solidity, a line in space where flow becomes sudden compression. At that boundary, some of the wind's directed energy is converted into random particle motion. The gas can become very hot, but the heat is not automatically shared with everything nearby. If the density remains low, hot particles can coexist with cooler dust grains that radiate efficiently. The environment becomes layered again, not by distance, but by coupling, by how effectively different components exchange energy. Magnetic fields add another layer of subtlety. Charged particles do not simply drift. They spiral along field lines, confined and guided. Energy can be stored in magnetic structures and released through reconnection, accelerating particles and heating plasma in bursts. This can happen far from the star's surface, in regions that look quiet in visible light. It means that even where sunlight is weak, local processes can keep certain particles energized. The mind expects cold to deepen steadily with distance. The cosmos allows pockets of kinetic heat to persist like embers, not because the region is dense, but because fields can concentrate and redirect energy. The star's influence also extends through time in ways that are easy to overlook. A star can flare, shedding radiation in pulses. It can vary in wind strength. It can move relative to surrounding clouds, changing which regions are exposed and which are shielded over long spans. A region's temperature, especially for dust and gas with long equilibration times, can reflect not only the present radiative environment, but the history of exposure. Cold can be a memory, and warmth can be an afterimage, lingering in the thermal inertia of matter. And there is another kind of secret heat, one that is not carried outward but stored inward, the heat that bodies accumulate and release slowly. Planets, moons, asteroids, even sparse rings of debris can hold thermal energy and re-radiate it. Near a star, these bodies intercept starlight and then glow in infrared, becoming secondary sources of radiation. A small region of space can be warmed not only by direct starlight, but by the thermal emission of nearby objects. In crowded systems, the sky is not a simple background. It is a mosaic of radiative surfaces. This matters because the coldest conditions often require an unobstructed view of the coldest sky. Any warm body nearby fills part of the sky with infrared light, raising the equilibrium temperature of surfaces that face it. In that sense, deep cold is not just distance from a star, but distance from everything that has stored or is emitting heat. It is a kind of radiative solitude. Around stars, solitude is hard to find because stars create systems, and systems create many secondary sources of glow. Still, within these systems, cold persists, not as a uniform blanket, but as carefully placed quiet. The night side of a slowly rotating body can fall into a deep chill. The interior of a shadowed crater can maintain low temperatures because it rarely sees sunlight. The densest regions of a molecular cloud can remain cold because their own material blocks external radiation. These are not exceptions. They are the natural outcome of a universe where heat is delivered by line of sight. When you hold this picture steadily, you begin to see why stars can be closely linked to cosmic cold. They create the strongest gradients. They supply the energy that makes shielding meaningful. They drive winds and expansions that thin and cool material. They compress gas into structures that block and filter light. In a universe without stars, space might still cool, but it would lack the sculpted complexity that allows cold to gather in protected pockets while heat continues nearby. A star's neighborhood is therefore not merely a zone of warming. It is a dynamic environment where heat is continuously redistributed into light, motion, and structure, and where cold emerges wherever energy pathways narrow. The paradox is not that cold exists near stars. The paradox is that cold can become stable and influential in a region dominated by a luminous source, simply because the luminous source does not heat everything equally. The most calm and enduring truth here is that warmth is never guaranteed by proximity alone. It is guaranteed by connection. In space, connection means absorption and emission, collision and coupling, view and shielding. Around stars, those connections are constantly being made and broken by motion, by density, by field lines, by geometry. The result is a universe that is neither uniformly warm nor uniformly cold, but quietly patterned, its temperatures written into the arrangement of matter. And as that pattern becomes clearer, the idea of how cold space can become begins to feel less like a single extreme and more like an ongoing negotiation, not between human comfort and cosmic hostility, but between energy and the routes it can take. The secret heat around stars is not only what they give off, It is the way their presence organizes the universe into places where heat travels freely and places where it cannot easily arrive at all. The first problem with measuring cold in space is that you cannot hold space still long enough to touch it. You can only watch it, and you can only watch it through what it gives off. In the universe, temperature rarely announces itself as a simple sensation. It arrives as a faint bias in a spectrum, as a slight shift in the balance of light, as a softness in the glow of dust, as the way a molecule chooses one energy state over another. The coldest places do not look cold, they look quiet. A thermometer on Earth is a device that waits for agreement. It becomes the same temperature as its surroundings and reports the compromise. But in space, agreement is often exactly what does not happen. A sensor can float through gas so thin it barely collides with it, while the sensor's own temperature is set mostly by sunlight and shadow. Even if the gas is hot in the kinetic sense, it may not be able to share that heat with the instrument. So measuring temperature in space is less like dipping a probe into water and more like decoding a language, where every number is inferred from a clue. Light is the main clue, and it is more precise than it first appears. A warm object radiates more strongly and at different wavelengths than a cold one. A dust cloud, for example, can be mapped by its infrared emission, each region revealing a different balance of absorption and re-radiation. If the glow peaks at longer wavelengths, it is cooler. If it shifts toward shorter infrared, it is warmer. This is not merely color. It is physics written into the distribution of photons, and it lets us take the temperature of matter we cannot reach. Gas tells its own story through lines, thin, specific frequencies where atoms and molecules absorb or emit. These lines carry information about motion, density, and excitation. When gas is warmer, its particles move faster, and those motions broaden the lines in characteristic ways. Populations of molecules across energy levels also hint at the environment. In denser regions, collisions can shuffle molecules into a thermal distribution that reflects kinetic temperature. In thinner regions, radiation can dominate the excitation, and temperature becomes more complicated. Astronomers learn to read the difference, to separate what collisions suggest from what light alone might imprint. When the goal is the coldest environments, two kinds of measurement become especially important: the faint glow of the coldest dust and the whisper of the coldest radiation that fills space itself. Dust in dense, shielded clouds can cool to remarkably low temperatures because it sees little starlight and radiates efficiently. To detect it, instruments must be sensitive to far infrared and sub-millimeter wavelengths, where cold dust emits. What appears as a dark patch in visible light can become luminous in these bands, not because it is warm, but because even cold matter must radiate. Yet the most inescapable temperature in the universe does not belong to dust or gas. It belongs to the background glow that comes from all directions, a relic light stretched by expansion until it sits in the microwave. It is faint enough that human senses would never notice, but it is real enough to set a universal baseline. You can travel away from stars, away from galaxies, into the emptiest voids, and that glow remains. It is not a local weather pattern, it is a property of the cosmos. The discovery of that background was a turning point in how we understand cold space, because it revealed that darkness is not blank. The universe carries an ambient radiation field everywhere, and any object that can absorb and emit will, over time, tend toward balance with it, unless another source of heating intervenes. That means, how cold can space be has a floor that is not defined by emptiness, but by history, the afterimage of a hotter, denser universe that still drifts through the present as a faint sea of photons. If you ask where the coldest matter we can observe tends to be, the answer often points to places that are both dense and hidden: the interiors of molecular clouds, the protected regions where starlight is filtered into long wavelengths and energy exchange becomes slow. In these regions, temperatures can fall low enough for certain molecules to form and persist, low enough for dust grains to carry thin mantles of frozen material, low enough that chemistry becomes deliberate. The clouds are not cold because they are far away. They are cold because they are shielded, because they sit in their own shadows. Within these environments, cold is not uniform. Even a dark cloud has gradients. The edges, exposed to the galaxy's diffuse starlight, are warmer. Deeper inside, where radiation struggles to penetrate, temperatures drop. The coldest pockets often lie in cores, dense knots where gas and dust are concentrated. These cores can become the seeds of future stars, and in that sense, the coldest places are not merely remote, they are preparatory. Cold is a condition that allows matter to settle, to reduce pressure, to become willing to gather. But there is another category of cold that does not depend on shielding. It depends on isolation in the most literal sense. Regions of space where very little radiation arrives and very little matter is present to hold or distribute energy. In the vast spaces between galaxies, the radiation field can be minimal aside from the universal background. If you place a free-floating object there, far from any star, it will cool by radiating away its internal heat until it nears equilibrium with that faint glow. The process is slow, but it is steady. Over time, such an object becomes a kind of thermometer for the universe's baseline. Still, even the emptiest regions are not perfectly quiet. Energetic particles pass through. Distant galaxies contribute a thin, diffuse background at various wavelengths, and the universe's own structure creates occasional shocks and heating events, even in the spaces between. The coldest possible state is therefore not a simple matter of going far enough. It is a matter of removing sources of heating so completely that only the unavoidable remains. And what is unavoidable is not only the background radiation, but also the rules of physics that prevent perfect stillness. Absolute zero is a concept that draws a boundary around what temperature means, but it is not something the universe offers freely. Even in the most carefully controlled experiments on Earth, reaching closer and closer to that limit requires elaborate isolation and sophisticated techniques, and the last steps become harder and harder. In the open universe, where stray photons and particles always exist, the limit is not just difficult, it is asymptotic. So when we speak of the cold we can never escape, we are speaking of two kinds of inevitability. One is cosmological, the ever-present photon field that bathes the universe and sets a baseline temperature. The other is physical, the way matter itself resists being pinned to perfect stillness. Together they define a floor beneath which cold becomes less a measurable state and more a mathematical ideal. Yet it is important to notice how gentle this inevitability is. The background glow does not roar. It does not announce itself. It is simply there, woven into the sky. And the quantum restlessness of matter is not a chaotic agitation, but a quiet constraint, a minimum energy that cannot be negotiated away. These are not dramatic limits. They are calm ones. They do not forbid the universe from becoming very cold. They simply prevent it from becoming perfectly cold. All of this changes the meaning of measurement. When astronomers assign a temperature to a cloud, a void, or a radiation field, they are not claiming a universal ambiance that everything shares. They are describing a specific component, dust, gas, photons, under specific assumptions about equilibrium and coupling. The coldest temperatures we quote are often the coldest of one component, under conditions where that component is best isolated from heating. In this way, the coldest space we can reach is not just a place, it is a situation, matter that can radiate, shielded from light. disturbed rarely enough that it can settle toward the faint baseline of the cosmos. And the cold we can never escape is not a punishment. It is a quiet reminder that the universe always contains something. A thin bath of radiation, a minimum motion, a trace of its own beginnings. When measurement becomes inference, the universe begins to feel less like a landscape and more like an archive. Every temperature we assign to a distant region is a reading of what has been allowed to happen there, what sources of energy have reached it, what pathways have carried energy away, and how long those pathways have been available. Cold, in this sense, is not just absence. It is history written in slow physics. The coldest environments we can identify are often those that have been quiet for a long time. Not necessarily untouched, but undisturbed in the specific way that matters for temperature, free from sustained heating, and able to radiate into a sky that does not return much. In dense, dark regions, that quiet can persist because matter itself forms a shield. The dust and gas become a kind of self-made night, blocking sharper radiation and letting only the gentlest wavelengths filter through. In such places, the path to deep cold is not dramatic. It is simply open. A cloud core cools not because it is trying to become cold, but because it is allowed to emit. Molecules radiate energy away in narrow lines. Dust grains glow faintly in the far infrared. Each photon that escapes carries a small portion of the internal energy with it. Over time, the remaining energy pool becomes smaller. The temperature falls. What makes these regions valuable to science is that they show cooling in its most patient form. Not a sudden plunge, but a long drift toward equilibrium under scarcity. Even then, equilibrium is rarely perfect. Inside a single cold core, different particles can behave as if they live at different temperatures. Dust can be colder than gas, or in denser regions, dust and gas can couple more tightly and share temperature more effectively. Some molecules can be more sensitive to radiation fields than others, making their excitation temperature diverge from the kinetic temperature. These distinctions are not complications added by scientists. They are the real texture of a low-density universe, where the old assumption, that everything nearby shares the same thermal state, no longer holds. This is why the coldest numbers we read in astronomy carry an unspoken humility. They are not simply the temperature of the place. They are the temperatures of specific tracers, derived from how those tracers interact with light. A far infrared glow tells us about dust. A molecular line tells us about gas under certain assumptions about collisions and radiation. A background spectrum tells us about the photon field itself. Each one is a different witness. And among these witnesses, the most universal is the background radiation that fills all space. It does not care about clouds or voids. It persists in interstellar gaps and intergalactic reaches alike. It is, in a way, the closest thing the universe has to an ambient temperature. Not because it forces everything into equilibrium, but because it is always present as a minimal radiative environment. This background sets a kind of gentle limit for ordinary matter. If you were to take a small, isolated object, one that absorbs and emits efficiently, and place it far from stars, it would radiate away its stored heat until the outgoing emission matched the incoming background. In the deep quiet, that balance would define its temperature. The object would not feel cold as we mean it, because there is no sensation, but it would become a physical testament to the universe's baseline glow. The limit here is subtle but important. The background does not stop something from cooling, it slows the final approach. As the object becomes colder, it emits less power. Each further step downward takes longer. The object is not prevented from cooling below a certain temperature in an absolute rigid sense, especially if it has unusual properties or is engineered to reflect and emit selectively. But the background sets a persistent, unavoidable inflow of energy at certain wavelengths, making the deepest cold a matter of asymptotic balance rather than a clean finish line. This is where the phrase, "the cold we can never escape," gains its true meaning. It is not that the universe holds us at a comfortable minimum, it is that the universe never fully empties itself of energy. Even if matter becomes sparse, even if stars are far away, even if a region seems visually black, there remains a faint radiative presence. The cosmos is not a perfect vacuum in the thermal sense, because it still carries light, still carries the residual warmth of its own early state. And that early state is the deeper story beneath the measurement. The background radiation is the cooled remainder of an era when the universe was much hotter and denser, when light was not a traveler passing through empty space, but a participant in a thick, bright medium. As expansion stretched space, it stretched the light with it, lowering the energy of each photon. In doing so, the universe cooled its own radiation field. The baseline temperature of space, then, is not a local accident. It is a slow consequence of cosmic growth. This introduces a strange and calming perspective on cold. The coldest space is not fixed. The universe's baseline cools with time. Given enough cosmic patience, the background radiation will become even fainter. The temperature associated with it will drop further. In that far future, the floor will be lower than it is now. But it will still not be nothing. There will still be a distribution of photons, however sparse and however stretched. The universe will grow quieter, but it will not become perfectly silent. Meanwhile, other sources of energy remain, even in the long term. Radioactive decays and particle interactions can deposit small amounts of heat into matter. Gravitational processes can release energy when objects fall together or when orbits shift. Even a rare collision over immense timescales becomes inevitable. The universe does not easily allow a system to be perfectly isolated forever, and isolation is what absolute zero would require. No incoming energy, no internal residual motion, no events that disturb the final stillness. This is why the deepest cold in nature is often found not in the emptiest spaces, but in specific protected circumstances where matter is present and able to radiate efficiently while being shielded from heating. It is also why, even when we can identify cold regions, we speak of them in terms of their components. A cold dust core can sit inside a broader region where gas is warmer. A void can have a low radiation environment while still containing particles with high kinetic energies. The coldest value depends on what you choose to measure. And yet, despite these layers of meaning, the core insight is simple. The universe is cold not because it is trying to be cold, but because expansion and radiation make cooling possible. Heat is concentrated in stars, in warm planets, in active environments. Everything else spends its time radiating away the energy it has, returning it to the sky. Over long times, that process dominates. It is the default direction, the quiet arrow drawn by thermodynamics into the fabric of a universe where light can always leave. What makes the cold we can never escape so significant is that it reminds us that even empty space is an environment. It is not a void devoid of properties. It has a radiative character, however faint. It contains fields and background photons. It supplies a minimum context in which matter exists. No object is truly alone, because the universe still has a glow, and physics still imposes constraints on stillness. In this light, measurement becomes a kind of humility. We do not claim to have touched the coldest regions. We claim to have read them carefully through the signatures they send. A line in a spectrum, a faint emission peak, a slight imbalance in photon energies. These are how cold becomes visible. And the act of reading does something subtle to the question itself. It turns "how cold can space become" into a question not only about extremes, but about what is fundamentally unavoidable. It asks what remains when everything else is stripped away, when stars are distant, when matter is thin, when energy exchange is rare, when the sky is almost dark. The answer is not a single number. It is the recognition that cold in the universe is bounded by gentle persistence. The persistence of radiation, the persistence of physical limits, the persistence of history. And perhaps that is what this final chapter leaves behind as a quiet conclusion, without needing to announce it as one. The universe allows great cold, deep enough to slow chemistry and soften motion into stillness. But it does not allow perfect cold, because perfect absence is not part of its design. Even at its quietest, space carries a trace of its beginnings, and even at its coldest, it holds to a baseline that cannot be entirely erased.